Hello friends, welcome to my channel. Let's have a look at problem 322 again, coin change. So in this video, we are going to share solutions based on dynamic programming with or without memorization. So in a previous video, actually we practiced this classic problem using breadth first search. So that's actually also a natural solution. You are welcome to check that video out. So here, for this problem, before we go to the analysis, I want to emphasize 2 points. First is that for each coin, we can use it multiple times. So secondly, the array length of coins is bounded above by 12. So with that said, let's look at the methods. So here we're going to present DP solutions. So the plan is as follows. First, we're going to write a dynamic programming solution with cache. So we shall use a hyperfunction with cache functionality here. So, and the format actually is routine. So, and the interpretation is like plain English. So this is the first part. The second part is that we want to write a DP solution with tabulation. So here, for the DP table generic element, DPI, we shall interpret it as the minimal number of coins to sum up to the amount I. Then we want to specify the DP update rule based on comparison. So this line specifies the DP update rule. So DPI is the minimal of DPI minus coin plus 1 and the DPI state for all coins such that I is greater than or equal to the coin. So here, DPI minus coin means the minimal number of coins to break the amount I minus coin, right? So then we increment by 1. So this provides a way to break the amount I, right? So that's the plans for with 2 parts. So next is some suggestion. First, so actually it's good to compare the problem here with the combination sum problems. So the analogy is the following. Those problems are all concerning the task that we break a target into pieces, but with different requirements and return formats. So actually the ideas are quite similar. So typical solutions or methods are dynamic programming, traversal, or backtracking. So with a set comment, it's also good to compare this problem with the knapsack problem. So there are some loose analogy here. So with that said, let's look at the solution to carry out our plans. So first, we are going to write a solution based on using cache, using memorization. So for this, I'm going to write a hyperfunction. I'm going to define this function as f. So here it accepts 2 arguments. One is total, the amount of money we are going to break using the coins in the coins list given. And we are going to specify a cache. So here. So notice that cache is defaulted as a dictionary. So dictionary is mutable in Python. Therefore, we can continuously update the using the updated state of the cache. So that's the function signature. So the role of this function is find the minimal number of coins needed to break total, right? So that's the function. So for this, actually it's very standard. So first we check some stop conditions. So if total equals 0, means that we finished the break for the total. So we are going to return 0. So that's a special case. And here we want to notice that the coins actually is greater or equal than 1. So if we have 0, we should return 0, not 1. And that's another condition is if total is less than 0. So we're going to return -1. So this -1 actually is related to the problem requirement here. So that's another one. And then we want to take into consideration of the cache in the argument. If total in cache, then we're going to return cache total. So the cache will store the amount and the corresponding minimal number of counts needed to break that amount. So these three ifs are actually stop conditions, so it's very standard. So next, let's do the genuine work. So we're going to initialize a variable called inCounts. So because we are going to find the minimal and we want to use comparisons, so we are going to set this to be the largest possible one. And then we are going to traverse the counts for count in counts. So notice that we are looking at all the counts because each count can be used multiple times. So with that said, we are going to make a recursion call. So for call f and the total minus count. So we want to break this amount. So then put the current cache state. So then we want to try to add this result to the cache. So first, if the temporary is not -1, that is, it's greater than or equal to 0, and less than the inCounts in the previous state, then we are going to set the inCounts to be temp plus 1. So after this for loop calls, actually we shall set the state of the in the cache for the amount given, that is total. So basically cache and total will be the inCounts, and then we are going to return inCounts. So that's the hyperfunction. So here we have a cache, so we are using the dictionary. So this way of presenting the solution actually corresponds to add some decorator here if we do not use, so for example cache, so if you like. So but this way actually help us to understand the mechanism of that decorator, I would say. So with that said, we are finished the main work. So let's call this step 1, preparation for a hyperfunction. Secondly, we are going to prepare the result, the return. First, let's call this function. So we are going to call this as a result. So function. So initially we have amount, right? So the cache is initially empty. So this is the amount we want to return, but we need to check if this result is positive infinity or not. If it's positive infinity, means that we cannot successfully break the total or the amount using the current given counts. So we should return -1. So then we're going to return result if result does not equal to float infinity. The same we set here. Otherwise, we're going to return -1. So that's one format of solution. Let's do a quick check. Yeah, it passes example 1. Now let's look at generic case. Yeah, it passes the generic case. So this is one format of solution. So let's use this as V1, and then we write another solution. So in the second solution, we are going to use a DP table. So for this, first, we are going to set this one to be 0 plus float infinity times the length, not the length, the amount, right? So in other words, this DP list contains amount plus 1 elements. So the meaning or the interpretation is the following. So let's see. So DPI, so as we read above, so the number of counts in counts to break I. So we would say minimal. So if its amount is 0, so we need to return 0. The reason is here. So the cons is greater than or equal to 1. So next, basically, we just need to iterate for the cons and do the DP update. So specified here. So for in cons, and then so we're going to, if we want to use this con, we want to make sure the amount I is no less than this con. So for I in range and con, then amount plus 1, right? So then we're going to update this DPI by the minimal of DPI, its previous state. And if we want to use this con once more, so we're going to correspond to I minus con, and the number of cons should be incremented by 1, right? Counting this con. So this is the DP update rule. So after this inner for loop, we finish the reset of the DPI state. So then we are going to do the return. So what we want to return is actually DP amount or DP negative 1. So it depends on if DP amount does not equals to float infinity. Otherwise, we are going to return negative 1, same as above. So now let's do a special case check. Yeah, it passes the first example. Now let's do a generic case check. Yeah, it passes the generic case. So let's call this one V2. So we can actually check this first one again. This should be reasonably fast, because actually, so though we have 2 for loops here or 1 for loops here, so the amount, the length of the cons array is actually bounded above by 12. So essentially a multiple of 12 for the unit operations in these 2 solutions. So with that said, I guess that's about it for these 2 formats of solution. Thank you very much.